differentiation or anything, and you can build this function. And we talked about how you could take the derivative of that function recursively really easily. Derivatives are really easy. What about integrals? Could we take an integral like that? Anybody remember integrals? You might remember integrals are hard. Integrals are hard. I took this advanced class at Waterloo that told you how to write a program to take the integral of anything, and I would like to kind of relearn that because I never really understood it in the first place. But and then as we were running out the door, we looked at the simplification program. Right, we started with this, and we took the derivative of it, and it became something big. And the reason it became something big is because we have various, the divides in it. I don't know, it became big. And sometimes you want to simplify it, and the way of simplifying it is, again, often just doing it locally, making local obvious changes, and recursion does the trick. So you have a friend simplify this, and you have a friend simplify this recursively, right? And then you look at your little top node. Remember when you're doing recursion on trees, you shouldn't look down into the tree. You should just look at your root and the advice that you get from your friends. So your friends have simplified this and this, and you see, hey, you know what? Do I have? Can I simplify using some obvious local rule? Does that make sense? Everybody kind of got that example? Now, one thing, when I first started teaching here, which was, I hate to say it, I'm getting old. It was a long time ago. I started here in '95. They told me to teach this first year 1B, the 1030 course, and it was before Java, and actually I wasn't even teaching here. I was teaching over at Atkinson, and they gave me no advice as to what to teach. So I just started teaching things which I thought were cool, and you think what I do to you guys is hard. I killed them. Killed them. I gave them homework assignments that I wouldn't dream of giving you guys, right? And they were in first year. So this here was one of the homework assignments, which you're given a tree, and you want to print it out in kind of sideways in a pretty way. And a couple of years ago, I was teaching this for 3101, and after the class, somebody said, life is just amazing because I was just told by my boss that I had to write such a program. And this is the output of what he wrote, right? So it's right? So you see the tree structure. So what we're doing is we're given a tree, and we want to print it out like this. And what makes it a little harder is you can't go into the screen right here and type that character. You have to type this character first, right? You have to type them like this, right? Because that's the way your typewriter works. And so you want to type this, and you can see, this is dividing of this tree and this tree, and so you do it kind of recursively, but it's a little trickier than it first looks. All right, so the obvious thing is you get the right friend to print first, right, and then you get your left friend to print, and in between, to print, hey, my root is the divide, so you print this little thing at the top. That's pretty easy, right? It gets a little trickier in that, right, so my, right friend, my left friend's right friend, I guess, needs to print this tree, right? Now, what makes it a little harder? There are two things here that makes it a little harder than just printing the tree. Anybody see the things that make it a little harder? Can I just give them the tree, for example? Right? Usually when you recurse, you just give people the tree and they do what they're doing. But can that guy print it with just the tree? No. What else does he need? Yeah, he needs two things. One, he needs to know whether he's a left child or a right child, right? So he knows whether to print this or print this, right? And then one thing that's going to be true above this is all these lines are identical. Right? All this is a line of text, and it's the same all the way down. Right? So we give him the tree. Why don't I get out of here? I might be standing in the way. We give him the tree. We tell him whether he's on the left or the right, and we keep pushing the button, hoping that life will be good. Right? Everybody kind of follow that? And so what his task is, we have to define the pre and post condition. Right? The precondition is you're giving him some string here. You're given whether he's a root or whether he's a left child or a right child, and you give him a tree. And what he's supposed to do is print the tree, and then if it's the left or right, he goes this way or this way. If he's a root, he just does that. And the string, he just tacks on the beginning of every line. And then, what happens? He has two friends, and his friends are given the left and right subtree. His friends are told whether they're the left friend or the right friend, right? And what are their strings? Well, this guy's strings is the same string as before with a bunch of blanks put in front. And this guy's string is the same as it was before, except this little branch here was put. Oh, yeah. Yeah, I guess up to here is the string, right? So this was the string that they had before, and he added on this blank, and here we added on this branch. That kind of makes sense? So, this wasn't so hard, but people had a hard time with it. Anyway, that was the whole program. And you can trace it out if you want and see what happens, but we're not going to trace it out. Any questions about that? All right, so believe it or not, in that first year program course I taught, I also made them do parsing. Why? Because parsing is my favorite algorithm of all time. It really is quite beautiful. Question?
Yeah, how much of that
None of it. Yeah, actually, the truth is, it's a hard question what you're saying. Right? What do you need to understand? And in some ways, let me say this globally. You think about the last test that you wrote. What of what I taught you did you need to know in order to write that test? Right? Well, you needed to know the steps. Right? You needed to know the steps cold. You needed to be able to do them. And you needed to know nothing else. Right? Right? Is that would you agree with that?
Yeah.
So why do I do all that other stuff? Well, they're examples of doing the steps. And now, the advantage of learning them is that, one, they're fun, it helps you learn the steps, and two, you will be given another problem, and if you have a whole collection of examples, then it helps you to build from them. Right? So, Will memorizing that last example, certainly I would say all the little details, I'm never going to ask little question. Oh, remember that program where you're supposed to print the tree sideways? What is that little tweak right there? I'm not going to ask you that. I'm not. Right? Might there be a question in which the problem is you have to do recursion on trees, and you have to have a feel for how to do recursion on trees, and maybe having this extra example would help? Maybe. Right? Gives you this extra example of how you have to give your left friend and right friend extra information, what kind of things you might be giving them, and you know what I'm saying? Was that a good answer?
Yeah.
All right. All right, parsing. All right, so parsing is elegant, If it wasn't for parsing, really, if it wasn't for parsing, computer science as you know it would just not exist. What is a compiler? Right? Everybody knows what a compiler is. You write something in Java, and what does the compiler translates it into machine code. Why do you need to do that? Well, because the machine likes machine code, right? And you like Java, right? Well, actually, I don't. But in theory, you like Java, right? I have programmed in machine code, and it's not pretty, right? It's really not pretty. You don't want to do it if you don't have to, right? So that's why compilers are great. And what does a compiler do? Well, it first parses. It first says, tries to get meaning out of the structure of what you've written, right? This is a loop, and it's a loop over what? And it's, right? Similarly, if you're writing in Word, and it underlines something in green, why is it doing that? It's because it has a parser which is trying to say what's the noun of your verb, what's the verb of your sentence, right? It tries to think about grammar, the basic grammar rules, and if it can't parse it using the basic grammar rules, then it complains to you, right? And the program that it uses to parse is exactly what we're going to cover right here, right? It's just your basic parsing. The other sort of personal story about compilers is that I never took a compilers course as an undergrad or as a grad student because I'm kind of like doing math, and I hate coding. Those courses were big, heavy coding courses, and I was kind of lazy and would rather sit around and do math. So I never took a compilers course, but when I graduated and got divorced, my son was in Toronto here, and I wanted a job in Toronto, and that, there was really, U of T wasn't going to give me a job, right? So there was really only York or what? So I applied to IBM, and IBM was going to hire me writing compilers, even though I didn't know what a compiler was. So that was kind of my link to compilers. Until this day, well, until beginning of the summer, I didn't know what a compiler was. And my son, who's now turning 18. Can you believe he's turning 18? He's going to Montreal. Why is he going to Montreal on his birthday? Anybody know why? Because you can drink in Montreal when you're 18. That's why they're going to Montreal on their birthday. But besides that, he had to do a computer science project, and I said, let's write a compiler. And so it was really quite easy. We just, in like 4 or 5 days, the two of us sat down and wrote this compiler, and all you did is parse and spew out machine code. It was so easy. It was so much fun. All right, so if you have a chance to taking a compiler course, I don't know, it might be a lot of coding, but for us, I guess I knew enough about parsing, it wasn't so bad. All right, so everybody ready for how to parse? Yes. Yay, it really is quite fun. All right, so what are we trying to do is we're given a string like this, and as input, and the output is a parse tree. All right. So what is the output? It could be, if you kind of figure out what's happening here, right? This is this times this, right? No, did I get the right spot wrong?
No.
Bracket in there.
There's a bracket in there. All right. Oh yeah. So there, that's your baby, right? So you could have the plus at the top with your left tree and your right tree, right? But here we're going to do it slightly different. We're going to say this whole thing is an expression, and an expression is the sum of terms, and a term is the product of factors. So we need a grammar. You took this in 2001, hopefully, context-free grammars, right? And so what is an expression? An expression is the sum of terms, right? It could be the subtracting of terms, but let's ignore minuses because we want to make our life easier, right? It's kind of the sum of terms. What is a term? A term is a product of factors, right? What is a factor? Well, a factor could be an integer. It could be the variable x. It could be an expression around brackets, with brackets around it. Everybody kind of buy that? Everybody kind of remember this? Right? First off, just that it doesn't really matter, but it's a little quiz here. Is this a context-free grammar?
No. It should be have n.
It's not actually, because this is kind of infinite here, right? I have, really I should, if I wanted to make it into a real official context-free grammar, I'd say an expression is either a term or it's a term plus an expression, right? And then you can unwind that to term plus term plus term. But here I'm going to, we don't care about that, right? It's a sum of a bunch of terms, right? The reason they did that is because they wanted each rule to be finite. And here this is kind of the union of an infinite number of rules. All right, so, right, this whole thing is an expression. y is because this is a term and that bit's a term, right? And y is, do I unwind this? No, I don't. All right, and why is this whole thing a term? Well, it's a term because it's a factor by itself. And why is it a factor? Well, because it has brackets around it, and what's inside is an expression. Right? And why is it an expression? Well, I guess it's this plus this plus this. It's 3 terms. Right? Everybody kind of follow that? And so this is what we're trying to build. So we're given this thing, and we want to build this parse tree. Right? And this grammar, actually this grammar, is, we're going to see, it has this property called look ahead once. And the look ahead once grammar says that for any, here we have a number of different rules, right? It could be a term, or it could be a term plus a term, or it could be a term plus a term plus a term plus a term. If you compare any 2 of them, what's the first place that they differ is, in this case, is does it end or does it have a plus? Right? So it's a real character. So look ahead one mean I can tell the difference between these rules by looking at one token. Right? As I go along, it's one token. And that makes it a look ahead one grammar. And we're going to now talk about how to just parse look ahead one grammars. You just parse them in linear time. It's just about as amazing as it can be. Right? When we do dynamic programming, we will look at how to parse context-free grammars when it's not look ahead one. Then you're going to need something like in cube time. And if it's not context-free, when you all decide that you love me enough to take that 4111 course, I'm sure we'll look at how it's parsing in that case is undecidable. All right. So what did I say? That's about what we did. All right. So what we're going to do is we're going to write recursive code, and you should have known it's recursive. Why? Because we're in the recursion section of this course, right? And the first step in writing a recursive program is to be very clear about what your program's supposed to do. You know, what's your precondition, what's your postcondition, right? You write a really clear pre and postcondition. And the other really thing that you have to do is you really, really have to trust your friends here. Right? If you try tracing this out and worrying about what your friends are doing, you will die. Right? You're just right. So you trust your friends, you breathe a little bit, and you just hope that everything works out. Okay? So what do we want here? Well, the string, the input is a string and an index into the string. So the string here is the same string that you're trying to parse throughout the entire program. It never changes. You know, the reason we're carrying it around is because we don't like global variables. But you know, we're carrying it around with us, right? The I is an index into the string. All right. So what's kind of happened already is it's already been tokenized. So you know. Index here could be the integer 38, right? They've already decided that 3 and 8 is a token, but that's okay. And our goal is we want to parse the string starting from index I, and we want to return a parsing of an expression, and we want to get the longest expression. We want to go as far into the string as we can, starting where we are, the longest expression. That's a legal expression, and we want to parse that. All right, so if you didn't follow that, let's give a bunch of examples. All right, so if this is our string, and our index is right here, what's the longest thing starting from there that's a legal expression? The whole thing, right? The whole thing's a legal expression. Why? Because it's more or less the example we looked at before. I don't know if it is or not, but it's certainly a legal expression. Right? So if we give it this string, what it does is it returns a parsing of this string, which is exactly what we want. Right? That's our whole goal, is give it a string, you give it the index 0 or 1, it gives you the parsing. Right? Now, what happens if we started there? Remember, what is it? An expression is the sum of things. All right? So where can you see an expression? Right? That's a thing plus that's a thing plus. That's the thing. Where do we stop? Can we include this bracket? No, because the bracket messes up. Right? So that's what we would return a parsing of that. If we start there, then what's our parsing?
2.
Right?
2.
We get 2 plus, because expression is a sum of things, plus 42, and then we better stop. Right? Good. If we start there, what happens? Nothing. We just say, sorry, Butto, that, the empty expression is probably an expression too. All right. What's changed here is this used to be blue, and now it's orange. No, but it's also, before we were looking for terms, expressions, and now we're looking for terms. Right? So it's the exact same game as before, but we're looking for terms. And what are terms? They're things multiplied together. So what's the longest term here? Right? Multiplied together. Can we keep going?
No.
No, it doesn't. It's never heard of pluses. Right? Can't do that plus. So that's it. What happens if we start here? Can we get past this plus?
Yeah. Yes.
Yeah, because that's a thing that we would be multiplying together. That's a thing, right? So what about this plus?
Stop.
Then we get stuck. Everybody can see that? That's our biggest term. If we start there, our biggest term is 2. If we start there, we bomb out again. All right, now we're doing factors, right? So if we start here, what's our biggest factor? Factor is just either it's a thing or it's something complicated in brackets, right? So it's just the 6, right? If we start here, then it's the thing in brackets, right? If we're starting here, then it's just the 2. Everybody good? Then we got this. Oh, I guess that was a little fast, but it's that whole thing. You got the idea anyway. All right, so you're all probably thinking, come on, this code has got to be horrendous, but this right here, more or less, without any error checking, right? If you want to check to see if the person is giving you something wrong and have good error, give a good message, it might be more complicated. But this is the code. This is it. All right, so let's trace through this code and convince ourselves that it works. Suppose we're given this input right there. What do we want to do? Well, we start by saying, all right, I'm Mr. Expression, and what are my rules? Well, look at all the rules. All my rules start with term, right? Because it's a look-ahead 1. If they differ, they would differ in a character, but they don't start in a character. They start in a rule. So in a non-terminal, these are, remember, non-terminals? They all begin with the term, right? So what do we do? Yeah, who looks for a term? Don't work too hard here. You got friends. Who gets the term for you?
Your friend.
Get term. Get term, right? You ask get term to get you a term, right? So the very first thing you do is, here's a little error detecting, but you call get term. And what does get term do for you? Well, get term is very kind. Get term, we call get term starting from the same place. Right? Remember, we were blue, we were get expression, and get term was orange. So we start looking for a term from there, and it returns the biggest term, and it returns a pointer to here. Right? Oh, I forgot to mention that. It also returns a pointer to it returns the parsing and the index at the end. All right? So now we go back to our rules up there. We say, hey, that was great. We got a term. What's next? Well, what's next is either a plus sign or we're done. Right? So I look to see what's next. Right here I say, it's returning a pointer to the first character that wasn't parsed. right? I look at the first character that's not parsed, right? Here, get term gives it to me, right? Get term gives me the parsing and gives me the J after. I look at that character, right, and I say, are you a plus? And it is a plus, right? So I say, great, it's a plus. So then that means it's not that first rule, it must be this next rule. So what do I do now? I call Mr. Term again, right? We come back here, and we get the next term, and where's that term starting from? Right? We gotta move past the plus, right? So I call get term with the same string, but I move one past the last term, Mr. Term, gave me the first character after the term, first term, right? So which is the plus, and I want to go one past it. So we're now looking at the 987, right? So we call Mr. Term, and what does he give us?
4 to 3.
He gives us the next term, which is all the way up to here. Exactly. So he gives us that term, and he gives us a pointer to here. Right? We look at this and say, hey, is that a plus? Right? And it is a plus, so we call term again. And term gives us the next, I'll call term again, who gives us the next term. Right? And then again we look at the next character. And what's it? Is it a plus? No. Do I know anything about this character? I don't even know what it's called. So what do?
Exit.
I stop. Right? Great. We just stop. We jumped out of this. And then, now, in recursion, how does recursion work? Is you build sub-instances for each of your friends, which we did. We built sub-instances. They gave us answers. Here are the answers that they gave us. And now what we do is we take their answers and build an answer for ourselves. Right? So what are we building? We're building an expression. Right? And what does our expression look like? Right? That whole thing will be our expression. And what does it look like? It's an expression with the terms hanging off. And depending on whether you want to include the pluses in there or not, depends on your taste. Everybody kind of got that? Right? You could have either said this is a plus and not included these, or you could say this is an expression and you include these. So we just parse an expression. Everybody got that? Now, we do get term, it's just as easy. Right? We look, what is the first, the first thing we're supposed to do is we're supposed to get a factor. So, we call get factor, starting from where we started. And what does get factor give us? It gives us the first factor. And it gives us the J just past the first factor. Right? And then we say, okay, what's next up here, guys? And what's next is either we have a time sign or we bail. Right? And we look down here, say, what do we have? We have a time sign. Right? So we don't bail. And what do we do next? We need another factor. So we call get factor one past the times, and it returns to us that factor. Right? Everybody kind of good with that? And then again, we see what's the next character. Either it's a times or we bail, but we've never heard of it. Right? So we bail. And then we have to return a parsing of the term. And what will the parsing of the term be? It will be the term followed by the factors that Mr. Factor gave us.
But how is this recursion though? You're not giving the same, you're not calling yourself, you're just calling a different friend.
Very good question. Do you have an answer? All right, so everybody get the question, is what recursion is you call an example of yourself, right? So, and this isn't really recursion because get expression is calling get term, and get term is calling get factor. But who do you think get factor calls?
Get a term.
Expression.
Get expression,
Okay.
right? So is it, we have to open our definitions of recursion a bit, right? Or you could even have part of the input be another, it could be simply get. And you tell you an extra input here with whether you're getting an expression or term or factor, right? So that would make it clearly recursive. In fact, if you wanted to make this even more global, you'd say, it would be called parse, and what you would give it is a string and an index and the grammar rules, right? And you could give it whatever grammar rules you wanted, and it would automatically read the grammar rules and figure out who it was supposed to call and what it was supposed to do, right? And that would be kind of a universal parser. All right, get term. Now, get factor. All right. What do we do here? We look. What are our first rules? Well, we got two rules. One begins with an integer, and one begins with a bracket. So the first thing we look at is we look at the first character, and here we look at the first character, and if it's an integer, then what's our answer? We look down here. Is it an integer? Yes, it's an integer. Right. So what's our answer? Our answer is simply our parsing is that integer, right? And we move, and our j will be moving one past that integer. Everybody got that example? And otherwise, maybe this is what we're doing. We see, is it an integer or is it a bracket? Oh, look at it, it's a bracket. Right? So what do we do now? We say, oh, it's a bracket, so now we're supposed to call get expression. Right? So what we do is we call get expression one past the bracket. Right? That's where we move past the bracket. We call get expression, and bye. Come again. And what does get expression do for us? It returns that expression, right? And then, and it returns now we see what comes next should be a bracket. So get expression, return the pointer here. So we see, hey, is that guy a bracket? And if it's a bracket, in this case, yes, it is a bracket. If it wasn't a bracket, we would have an error message, right? But it is a bracket, so we parse. And what's our parsing? Our parsing is, well, it's a factor, which is the expression that Mr. Expression returned us with brackets around it. Everybody gonna buy that? Isn't that fun? And you can, so when we were writing a compiler, usually compilers make two passes through the code. The first builds a symbol table, and the second parses. And I didn't want to build a symbol table because that felt like it was going to be too much work. We wanted to write a one-pass parser, and it was surprisingly easy, as I said. And we parsed really most of Java, and it's just each little thing that's part of Java. You write code, and then when you're spewing out, you don't actually have to put out a parse tree. Instead of building the parse tree, you're spewing out machine code. So really what's happening is, there's all this recursion happening, but the value of the index, right, is just moving once through the string, right? So it's moving once through the Java code, and as it moves through the Java code, it was spewing out machine code, and it was amazing, but it worked. All right, so this is kind of what, and what was I saying here? And then if you looked at the tree of stack frames, you have an expression has the kids of terms, and then they have kids factors, and the parse tree, looks exactly like the expression tree, the tree, right? You called Mr. Expression, you called Mr. Term twice, and when this Mr. Term called Mr. Factor, and so forth. We're going to kind of follow that, and so back to what you're saying about is it recursion, if you want to prove how long this program takes to run and does it even stop, you have to make sure that the input is somehow getting smaller, right? And the way it's getting smaller is, if you start at expression, by the time you get back to expression, Is it smaller?
Yep.
Because why?
Because it's getting less.
Well, the only thing you know it's getting less is you remove the bracket. Right? Right? If we started with the bracket, for example, expression would call term would call factor would move past the bracket and call expression. Right? So that's how you know what you're doing is getting smaller. And if you play around with it a bit, you'll see that actually it's really linear time. It just flies through this string parsing. Everybody kind of good with that? Do people kind of follow that? Because you know it's going to be on the test. That was a joke. Yeah. No, it won't be on the test. I don't know what I would possibly ask you so that you could possibly get the right answer. So this is fun too. This was also, man, and maybe it wasn't all in the same term because I did teach it a couple of times, but I really did kill them. They wrote a parser and they wrote searching, depth first searching for cheese in a maze, and I got them to do this draw program. So this, but hey, do you know one thing I did good? This is one thing I did good, because I would think, I'm not a coder, right? I never took the compiler course. So I think, it's easy to code this out. And so I would assign them some program to code. But I thought, to be fair, I should code it myself. And when it took me 50 hours to code it up, then I thought, all right, maybe I should cut back a bit. And then what I would do is I'd give them blocks of my code and say, finish these code blocks. So it wasn't so bad. But yeah, they still died. All right, so now this is recursion. And actually this is a good thing to talk about now because Mandelbrot. People know who Mandelbrot is? He died. I didn't have, if you'd asked me last Friday, I wouldn't have known if he was alive or whether he died in the 30s, or in the, but I happen to know he's dead because he just died. All right, what did he do? He did fractals, right? And that's kind of what we're going to do now. Right, we're going to draw pretty pictures, and I needed a fourth, those fourth year projects? If you ever want to do a fourth year project, we could try to make something up. I've had a couple of them. One of them coded this up, and don't tell him, but he didn't do a very good job. So if, maybe we could even get someone to make it a little better. But you can find this on the web page, along with the slides. The page that lists all the slides of mine? Right next to recursion, there's a link to this program. So the input has two pictures and an integer. All right? And if the integer is 0, if the integer is 0, then you draw this picture, right? And if the integer is 1, then you draw this picture, and every time that you see this line with an arrowy thing in here, what you do is you rotate and shrink, and you recursively draw in there. So let's see what we're doing. So n equals 1 is you draw the square, and then in about here, you draw the circle. Right? It's a little smaller and a little rotated. You draw the circle, and so the circle is n equals 0, so you get the circle. Everybody got that? So memorize this picture. This is the n equals 1 picture. So n equals 2, you draw the square, and then you shrink and rotate slightly the n equals 1 picture. Remember what it looked like? Right? It looked like that. Right? So when n equals 3, you draw the square and you do the n equals 2 picture, slightly rotated and shrunk. Right? So n equals 30, you get pretty pictures. Right? Everybody see that? So you can see they keep rotating and spiraling inwards, and it's kind of fun. So in this program, you give it this program, you draw this picture, and you draw this picture. You tell it where to recurse, you give it a number, and it does this. And I tell you, if you don't think this out too much, what you get here is you know, but it's not so hard. All right. So here's another example. In honor of Minderbrod, my mom gave me a book years ago on fractals, and I'd never looked at it. But yesterday I sat down, and it was a big book, and I looked at every picture in the book. Yeah, but I don't think I read too much. But anyway, so this here is our base case picture, right? And this is a recursion picture. And what is our recursion picture? Is a vine, a stick, with little places to recurse off of it. All right, so n equals 0, you draw nothing, right? N equals 1, you draw the stick, and that's it, right? With nothing's hanging off of it. And the stick, you can't really see it there. N equals 2, you can see it a little better. It's a stick here with little sticks off of it, right? N equals 3 is a stick with little n equals 2's off of it. And n equals 4, and n equals 5. It's fun, right? You gotta admit it's fun. All right, so this is a classic one. This was in the book. Actually, the previous one was in the book, right? What's this is your base case picture is a line, and your recursion picture doesn't have any picture at all other than you recurse 4 times. All right? So n equals 0 is a line. N equals 1 looks like this, right? There it is down there. Right? Looks like this. N equals 2 is that bigger one. N equals 3 is that one. N equals 4 is that one. N equals 5 is that one. So here's a trick question. What does n equals 6 look like? Or n equals 7 or 8 or 9? It looks like that! Exactly! He's right! Why? It's because you can't get any more detail out of this thing. Oh, we're right! You're very good. You're very good. Let's see. We are going to be able to finish this topic in the next 5 minutes. All right, so here's a funny, let's go back a minute. Anybody know this example? If I go to n equals infinity, it's going to look basically like this, right? What's the length of the line? It's a line, right? The line's going to be infinitely long if you haven't. And that's what makes it a fractal, is that it has infinite length in a finite space. All right, so let's show that. We have recurrence relations. And actually, let me tell you right now, I'm going to just be honest with you. The test on Monday, it's going to require you to come up with a recurrence relation, not only for the running time, but a recurrence relation for something else. Right? You want to say, I want to measure some other property, and you need to come up with a recurrence relation, and then you need to solve the recurrence relation. Right? So recurrence relations just come up all the time, and you need to be able to do them. All right? So this is a fine example of where this will not be on the test, you know? But you will have to come up with a recurrence relation, and it won't be, the thinking about it won't be all that different than the thinking about this one. All right, so what's the thinking is what do we define this thing to be the length of this thing. Say that this distance, you know, this distance here is 1, right? What's the length of the whole curve when we recurse n times, right? So let's start, if this is 1, then how long is this? Well, this is a third, and we have 4 of them, right? So 1 is 4 times longer than 0. And you can kind of imagine that each time you recurse, it gets 4/3 times longer, because you take this picture here, and I shrink it down to a third. I scale it. It gets to be a third of the length, right? And then I put 4 of them down, and so it's 4/3 times as long. People kind of buy that? So now you need to be able to solve this, right? Could everybody solve this? You unwind it, right? every time this gets one less, you get one extra factor here, right? So you get 4/3 to the n. And you can check it here. Well, if n is 0, 0, you get 1. Right? Everybody kind of buy that? And as n goes to infinity, this very quickly goes to infinity. Okay, everybody good? How much time do we have?
2 minutes.
2 minutes. All right, we can do another topic. All right, so another thing they had to do in one of these first-year courses, and I did teach it a couple of times, is they had to generate a random maze, and then they had to use maze searching techniques to get there. And here's a door to the maze, and then it's a room, and here's a door to this room, which is a door to this room. It's kind of hard to see because they're all stars. One of the courses I taught was in C, which only did stars, and one did it in Turing, which was, I really like Turing, and it let you do graphics. But anyway, how do you randomly do a room? Well, you're given a room, and we want to fill it with walls, right? So how did we do that? Is we randomly chose a point here, randomly choose a point in this whole room, and you put walls here, and you put a door here. So there's a door, the only door was here to the room, and now you go through this door to get to this room, or to this room. Right? That's the maze. And now what do we do?
Recursion.
Yes, recursion. Not another room. That's wrong. That's right. Let's all talk to the first-year student. You recurse. Right? You have 4 friends, and you recurse. Right? Because you don't want to micromanage your friends. Right? You just get them to do it. Right? Everybody follow that? And you put the cheese in one of the random rooms. And that's it. And we'll do Ackermann's function next time. And in fact, I think Ackermann's function might be last. All right, so the next 10-15 minutes of next class will be Ackermann's function, and then we'll be done recursion, and we'll move on to graph, depth first search, breadth first search, network flows, and then we move on to greedy algorithms and dynamic programming, and we dig ourselves a bigger and bigger hole.
Look, what you want to